All right, it looks like everyone has audio. So good day, everyone, and welcome to today's webinar, Onboard Fast Flash Programming Technology Innovations, Addressing Offboard Challenges. My name is Alan Squigna, and I'm the Business Development Manager for Asset Intertech's Debug, Test, and Programming Portfolio. Today, you'll be hearing about Asset's onboard in-system programming solutions using several different JTAG-based technologies. But before we get started, I'd like to go over a few housekeeping items so you know how to participate in today's event. First and foremost, today's webinar will last approximately 40 minutes. During that time, you'll have the opportunity to submit text questions to today's presenter by typing them in to the questions page at the bottom of the control panel. You're able to send in your questions at any time throughout the presentation and demonstration. We'll collect these and address them during the question and answer session at the end of today's webinar. You'll also have the ability to respond to random polling questions that will pop up throughout the webinar, so be prepared to participate. And on that note, please be sure to download a copy of today's presentation, which can be found as a handout in the control panel of your screen. Now, without further ado, we'll turn the time over to our presenter, Larry Osborne. Larry is a product manager for Asset Intertech's Test and Programming Solutions, with a focus on our ScanWorks, FPGA, and processor embedded software-centric solutions. Larry has over 30 years of experience in embedded software product development and delivery, and prior to working for Asset, he held engineering and development roles with Lockheed Martin, Hewlett-Packard, and Wind River. So over to you, Larry.
Thank you, Alan, for that kind introduction. I appreciate it. Good morning, good afternoon, good evening. Today we're going to be covering the in-system fast flash programming technologies that Asset has to provide and offer. My goal for today's webinar is for you to come away with at least one piece of information that you can apply directly to your position and actions that you can take from this webinar. So with that, let's get started. Let's take a look at the agenda. First, we'll look at offboard versus onboard. Then we'll take a look at the trends we're seeing that are putting more and more pressure on development and production implementation of flash. SoCs, FPGAs, and software technology are all contributing to an increasing of programming times. We'll see how these trends are being addressed by Asset and what I call the ScanWorks programming toolbox. We'll discuss programming methods, where they apply to the correct technology for the best performance. And finally, a demo on the Zedboard Zynq-7000 Zedboard using all the different technologies. The first topic that needs addressing is why in-system programming. In the past, in-system programming was limited by JTAG-only methodologies, and it placed a limit on the image size that was acceptable for manufacturing beat rates. So pre-production was the accepted norm. That's not the case any longer. Inventory management is a thing of the past when megabytes of data can be programmed at near device flash specification speeds. Hassles with engineering change orders or ECOs due to extensive inventory can be eliminated. COVID has also brought about supply chain management issues. With in-system programming, constant software updates can be handled electronically without device changes, assuming that the image still fits. This is just one area that's changing. And now I'm going to hand it back to Alan for a polling question.
All right, thanks, Larry. I'll give me a second to launch this. Yeah, Larry's given us a little bit of an introduction to offboard versus onboard. And the question here is, are you doing offboard or onboard flash device programming? And first selection is offboard. Devices are pre-programmed separately. Second selection is onboard. Devices are programmed in situ, soldered down on the board. Or number three is a combination of both. So please go ahead and select the one that applies. And we'll give it a moment here. It looks like about 3/4 of the audience has chosen already. Give it another moment for the rest to weigh in. All right. Very good. I'll close the poll then. And it looks like 9% said Offboard, 64% said Onboard, and 27% selected a combination of both Offboard, doing both Offboard and Onboard programming. Back to you, Larry.
All righty, thank you, Alan. All righty, let's take a look at the trends. The trends are driving more single device complexity, whether it's artificial intelligence, 5G, ADS, or cyber. These generally means more software configurations required to power up, more software IP like AI is currently using in facial pattern recognition, and more open source software. Design cycles are getting shorter, but the amount of software within the designs are growing. SoC configurations with multi-core and additional cores like FPGA or GPUs are rapidly becoming a preferred adaptable platform, replacing ASICs and in some cases processors. The SoCs are homogeneous and heterogeneous. Examples are the ARM single or dual core like the legacy Altera devices, ARM v8 and ARM v7 architecture-based SoCs are adding FPGAs and other computing silicon. The market trends have driven Intel and Xilinx to bigger, more complex FPGAs. The SoCs are incorporating these more complex FPGAs, while the processor side can incorporate the latest processor silicon, but there hasn't really been any changes in the CPU area. However, in the next generation, that's changing as well, as there will be additional task-specific processor IP. This FPGA growth and complexity is now driving the changes in the design steps as well, where the silicon providers are adding new steps to cover power and thermal evaluations just after the synthesis for the design. Now I'm going to hand it back to Alan for another polling question.
All right, thanks, Larry. Polling question number 2 coming up. Are you having problems currently with Flash programming? If so, what? And there's a few selections here. Number 1 is it takes too long to program. Number 2, I don't have physical access to the Flash device. And thirdly, it's costly to reflash the part after it's soldered down. So go ahead, please, and submit your appropriate responses, and we'll wait to see until we have a quorum. All righty, looks like we have at this stage about 2/3 of the attendees have responded. Let's give it another moment here, and then wrap it up. All right, closing the poll then. 82% of the responses were it takes too long to program. 27% said I don't have physical access to the Flash device. And thirdly, 18% said it's costly to reflash the part after it's soldered down. Interesting results, Larry. Back over to you.
Yeah, very interesting. Thank you, Alan. Alrighty. So tools can only do so much for driving down programming times. The same is true for the Flash silicon technology. Flash silicon is now driving programming technology beyond serial quad to serial octal, but all the technology cannot impact programming cycle time if the designers don't reconcile the programming path within the design. In short, the design dictates the programming methods that are possible. Let's consider just a few items that impact programming. The questions posed here must be addressed early in the design cycle to address the programming speeds in development and the beat rate performance in production. If using an SoC, where's the Flash connected? On the processor side or the FPGA side? If using an FPGA, is there a system clock? Where does your boundary scan topology, what does your boundary scan topology look like? Is it designed for maximum throughput when flashing? How large is your code image? How many times will you reprogram the flash device while in development. We constantly work with customers that spend 30 or more minutes trying to program flash on a single device. That represents a significant cost in development and in production. So let's talk about ScanWorks. ScanWorks is a premier product test platform, but many users aren't familiar with the powerful toolbox provided for fast flash programming. The ScanWorks toolbox for programming includes boundary scan test, processor-based fast programming, and FPGA fast programming. The implementation of the UUT will determine the applicability of each of the tools. BST is JTAG based and thus needs JTAG and boundary scan enabled devices. PFP is an SoC based on ARM v7 or ARM v8 architectures and currently from NXP or Xilinx. FFP provides support for a variety of FPGA families from Intel, Xilinx, and Microchip, or what was formerly Microsemi. Also supported from the same vendors is the SoC implementations. ScanWorks Boundary Scan Test, or BST, is automated, model-based tool using an incremental test methodology to move from basic to complex in providing structural board test. Many improvements have been made in supporting and programming of flash devices, such as SPI, Quad SPI, Octal SPI, I2C, NAND, NOR, and embedded multimedia cards, or eMMC. PFX is a trio of tools within the ScanWorks platform that target specific engineering tasks to save development time, optimize memory performance, and promote better test coverage. These tools provide target resident agents to shorten the time frame between prototype and production when using ARM-based SoCs from Xilinx or NXP. Today, we're going to focus on the processor-based fast programming, or PFP. The processor-based fast programming is the tool that uses the processor within the SoC to program a suite of flash devices at near device speeds without a bootloader, an OS, or application present within the UUT. The FPGA-based fast programming provides flash IP used within the design as a powerful accelerator to reduce the programming times and costs. This addresses the growing complexity and size necessary to implement today's designs. I'm going to construct a UUT block diagram and then point out where the technologies are connected. This design begins with an SoC, and we're looking at the SoC from a programming perspective. Then I'm going to add an FPGA with a flash device and another standalone flash device. Now I'm going to add the boundary scan chain to connect the boundary scan enabled devices. Now I'm going to, add a SPI flash header and another flash device that's not on the scan chain. Next, we're going to connect a network connection to the UUT. And now I'm going to connect the controller to the UUT. Finally, I'm going to add the SPI Direct and the SPI DIO. I'm now going to map over this block diagram where the technology is most likely to apply. FFP covers the FPGA area, PFP covers the processor area, and BST covers the widest area. We never see a single target with all the technologies can be applied. Don't worry, we're going to break this design down further in the following slides. So starting with BST, as it's the most common programming model, but potentially it's the slowest. It all depends upon the JTAG scan clock rate and the size of the image to be programmed. Remember that the data transport for the image is JTAG, and the clock rate is determined by the slowest device within the chain. If the flash device is attached directly to the scan chain, or if it's connected to a device that has boundary scan cells, it's possible to program the device. I'm going to break out the SPI DIO and the SPI Direct on the next slide. SPI Direct and SPI DIO are two unique means of programming flash devices that are not in the boundary scan chain. However, it's up to the customer to enable the connectivity and create a cable fixturing that is required for either of these solutions. Not often do we see SPI headers due to board real estate constraints, but some customers have them. And if that's the case, the RIC 1400 can provide a SPI Direct connection for one of the fastest means of programming possible. The FPGA within the RIC 1400 supports the programming logic. The SPI DIO feature can be used with all the ScanWorks JTAG controllers. As the name implies, it's using DIO signals within the JTAG controller UUT interface. FFP is strictly targeted at FPGAs, but uses two methods to decrease the programming times. The first is short chain, where the FPGA is programmed with a boundary scan chain that supports only the needs for programming, 6 or 7 cells versus hundreds. The second method is flash IP instrument, where the flash control logic is programmed into the device and then embedded into the FPGA. The use of FFP can be applied to standalone FPGA or an FPGA with an SoC. Using FFP is a two-step process. The first step involves creating the instruments, mapping the pins, synthesizing the design, and creating the binary file. The second step involves programming the FPGA with the instrument. This will be covered in the demonstration. The FPGA SoC families that are supported are Intel Altera, Xilinx Zynq-7000, and the Xilinx UltraScale Plus, and the Microchip or Microsemi PolarFire, Fusion, Igloo, and Igloo 2 families. Not every device is supported within all of the families. PFP uses a similar approach. It uses the processor within the SoC and onboard RAM to execute IP that programs the flash device. The data transport can be JTAG or Ethernet. If the target has Ethernet, even a faster programming can be accomplished using a TFTP server that's executing on the host and the data transmitted to the processor via Ethernet. This essentially creates a big data pipe. Listed here is a gamut of slow to extremely fast programming options. It is, however, all driven by the board design, the image side, and the desired beat rate in the production floor. The best solution can only be determined by you, the customer. This chart is an example of what we have tested in development. In this chart, the T clock is the rate of the data transmitted via JTAG to the targeted flash device. And in the Ethernet example, the data is transferred via Ethernet and TFTP server running on the host. These measurements were not all made on the same target. However, after the demonstration, there will be a chart that has the recorded values of all the programming methods that used on the target. Alan, I think it's time for another polling question.
All right, coming up, Larry. The third poll is, would any of these faster programming solutions improve your throughput? And the selections are yes, no, or I don't know. So please go ahead and choose the appropriate response, and we're collecting them now. Let's see, we have approximately 1/2 of the folks have responded, so let's give it another moment. Okay, I think we can close the poll now. Oh, wait, a couple more coming in. All right, there we go. 64% said yes, 18% said no, and 18% said I don't know. Closing the poll, Larry, back over to you.
All righty, thank you. Interesting answers. So let's go into the configuration for the demonstration. We're going to be using a Zedboard with a Zynq-7000 SoC. The board supports the use of BST, FFP, and PFP. We've also added to the board a 32 megabyte flash on the PMOD connectors to support SPI Direct and SPI DIO. A little bit more about that in a minute. This is the ScanWorks RIC 1400 controller. This controller was used for this particular project, and it was chosen because it's the only controller that supports the SPI Direct. Here's a better picture of the target, so we can focus on the hardware detail. The red triangle indicates the only PMOD connected to the processor side of the Zynq-7020. The other 4 PMODs excuse me, are connected to the PL of the Zynq-7020. However, the one in blue will be used to demonstrate the FPGA fast programming on a 32 megabyte SPI flash device, and the one in orange will be used to demonstrate SPI DIO and SPI Direct via a header to a different 32 megabyte SPI flash device. We'll also be programming the SD card and the quad SPI, which is on the back of the target, using the processor-based fast programming. As I mentioned, the one in blue will be using to demonstrate the FPGA fast programming. And to accomplish this, we need to connect the flash FPGA, we need to connect the FPGA pins to the FPGA flash IP. This will be demonstrated within the demonstration. Excuse me. I just wanted to give everybody the opportunity to actually connect the dots in this as we go through this presentation. Okay. Alrighty, we're ready for the demonstration. This demonstration is pre-recorded to compress the time that's needed for some of the technologies that are not practical in the live demo. It also assists in avoiding any attacks by Murphy laws. One of the caveats for the GoToWebinar, the audio from the demo can only be heard through your computer speakers. If you have a problem hearing the audio, switch from your phone or your headset audio and use the computer speakers. Or you'll be able to hear the full audio from the recording that will be made available later. Now, let's get off to the excuse me, just give me a second here, and we'll get off to the demonstration. I hope everybody can see that, and here we go.
We'll start today's demo by launching ScanWorks and loading a project that covers all of the flash technologies provided by ScanWorks. Within the project, there are many actions. ScanWorks is a powerful tool for test and programming. We won't have the time in today's webinar to cover all the actions. As mentioned in the presentation, the design is using a Zedboard as the reference design. Let's look at the design. Here we see the JTAG primary path is a static path, and the first device is the DAP of the Zynq-7020 processor, followed by the Zynq SoC. If you're not familiar with the DAP acronym, it stands for the Debug Access Port. Access to the DAP is necessary for the PFP actions. We'll see this later in the demo. The first action is to verify the JTAG connectivity to the target platform. This action is Scan Path Verify. We execute the action and see the actual data matches the data expected, so we know we have JTAG boundary scan connectivity. Next, we run a standard JTAG programming action. We'll show the elements that define the action. The definition provides the name, the target device, the programming model to be used. We will also review the device access configuration. Here we map the flash device pins to the appropriate pins of the SoC where the flash device is connected via the PMOD header. Next, to select the image to be programmed, we'll set the start address and the end address to program 1 megabyte of data. Now to check the necessary operations. We check the manufacturer's ID, the device ID, erase the used sectors, then program the SPI device. That completes the action definition. Now we'll program the device. In an effort to save some time, I'll use a video trick or two to speed up the programming. If you're not familiar with JTAG programming, we're using a 30 megahertz JTAG clock, and it took nearly 10.5 minutes to program 1 megabyte of data. In the next example, we're using SPI DIO action. This action we're connecting to a header on the PMOD as shown in the picture. As we did in the first action example, we will need to address the configuration parameters, the name, the source file, the programming parameters, and so on. You notice that this configuration dialog is different. In this case, we are connecting directly from the RAC 1400 JTAG DIO signals to the flash device via a header. The configuration access shows we are using 4 DIO signals and connecting them directly to the programming pins of the flash device. Again, we need to check the necessary operations. We'll check the manufacturing ID, the device ID, erase the used sectors, and then program the SPI device. That completes the action definition. We're now ready to run the programming action. Remember, this action is still only using JTAG, so again I'll use some tricks to shorten the time it takes to complete the process. Programming via DIO only took 1 minute and 22 seconds. This is a substantial improvement. The third and final BST programming action is SPI Direct. We will still need to configure the action, but you should recognize the steps by now. Here we connect the target to the REC 1400 SPI header. This path and action enables the use of the FPGA within the REC 1400 to program the flash device. You can see the action connection to the target is included in the picture. No alterations of the video is required for this programming action because of its speed. Now we'll run the action. Using SPI Direct, the programming of 1 megabyte of data takes exactly 1.23 seconds. This is the fastest programming technology available. The next action is using the FFP short chain. There are 2 separate steps required. Before we can use the short chain within the FPGA fabric of the Zynq-7000, we have to build the instrument and then load the instrument. The second step is to build the programming action. We start by checking to see if the synthesis tools are configured. This design requires the Vivado tools from Xilinx. The synthesis tools are not provided by Asset. We won't cover the project creation, but training is available. We start by opening the embedded tester. In this case, it's ET0. You can see in the project view that the design is complete, but we should review a couple of the settings. Next, we select the instrument instance of short chain. Then we inspect the configuration parameters for the short chain, checking the inputs and outputs. Then we check the pin maps between the port names and the FPGA pins. Next, we generate the wrapper. This step instantiates the instrument library Verilog files that we distribute with ScanWorks. We are now ready to synthesize the design and generate the SVF. The SVF is the image that contains the short chain for the FPGA. Once again, video tricks will be employed. If you're curious, the synthesis took 7 minutes and the SVF generation took another 2 minutes. This completes the instrument creation. Back to the action. We need to build the action that will load the FPGA image. You have seen this process in other actions where you select the image to be programmed, so I won't narrate each of the steps. The important part of this build is getting the ET0 instrument SVF file we just created in the previous step. This completes the 2-step development process to prepare the FPGA for use in accelerated JTAG programming. Now we need to execute the action to program the FPGA. At times it's easy to get lost in the action steps, so I've included a graphic that shows what we've just accomplished. We have just changed the JTAG scan chain from hundreds of cells to just 7. The next action is needed to program the flash device using the FPGA with the short chain IP. We need to verify that the configuration elements are correct, including the target device, the model used, the operations, and the device access map, and finally the correct image. Finally, we program the SPI device using the shortened chain length. We see a substantial improvement in the programming throughput. This took approximately 2 minutes. The next programming action is using the SPI flash IP. We need to get back to the FPGA development section and create the flash IP instrument. We have similar steps as we did in the short chain, which used the BSTIO IP. The SPI flash instrument is different in that we are not manipulating the scan chain, but rather putting control logic within the FPGA. The embedded tester for SPI Flash is ET1, which has already been selected. We need to select the SPI Flash instrument and examine the parameters and the pin map, which is different for this instrument. The parameters control the sysclock polarity and phase relationship to the SPI interface. The pin assignment configures the port direction and names to the FPGA pins. The setting of the I/O pin type is also critical for this step. Once the review is complete, we generate the wrapper, do the synthesis, and generate the SVF file. Again, I'll employ video tricks to save some time. Now that the synthesis is complete, it's time to generate the SVF file. We completed the steps for the IP generation. Now back to the action development. We will need to take the SVF file we just created and program the FPGA. The development steps are the same as all the others. The important steps to ensure we include the correct SVF. We run the action to program the FPGA. Again, I've included a graphic that shows what we have just accomplished. We have programmed the FPGA with the Flash IP. Now to configure the action that will use the Flash IP we just installed in the FPGA. The sequence of steps are similar to all the other Flash actions we have seen thus far. There is one additional step, and that is to import the instrument map. The instrument map provides for network order determination and for the hardware pin associations for test control. We'll now execute the SPI Flash action to program the 1 megabyte of data. The programming took 3.4 seconds. This completes the section working with the ScanWorks FPGA programming technologies. Next, we will implement the programming using the processor-based Flash programming tool. Like the FPGA tool, when we edit the action, it opens a separate interface that deals with the processor. The PFX developer provides the template to support the types of Flash devices. Here we program the quad SPI via JTAG. One of the first steps is to configure the SoC multiplexed I/O pins. Each of the SoC vendors provide tools to initialize the SoC. The outputs of these tools are C source files. We convert the initialization source code to a script and use that to initialize the SoC directly. In this case, we're initializing the quad SPI controller. The next step is to provide the data as parameters that need to be configured from the quad SPI datasheet, as shown here. The final step in the configuration is to determine which programming actions are required. For this action, we'll do some testing before we program. The tests include the device unlock, unprotect, erased, and blank check. We're now ready to program the quad SPI. Selecting Connect downloads the target agent into the SoC and initializes the processor. Selecting Run will execute the series of steps that we just configured. In addition to the test, we set the CPU clock to 800 MHz. We now program the device. The JTAG interface is providing the data stream to the target agent. The programming and checksum is complete. The programming took 8.7 seconds, with a throughput of 116 kilobytes per second. Now back to the actions to program the 1 megabyte image using the Ethernet as the data pipe. We start by editing the action. Here we see a different target agent will be used, and the only configuration change is the program operation where we're using the TFTP as the source rather than a file as we did in the previous action. We need to configure the settings for the TFTP server. These settings include the PHY address, the MAC address, the target IP address, the subnet mask, and the server address. Now to start the TFTP server on the host. Notice that we are tracking the server status. Selecting Connect downloads this target agent to the SoC and initializes the processor. Selecting Run will execute the series of steps just as before. However, the network will serve as a data pipe for this Ethernet programming action. The programming is complete. Using the Ethernet as a data pipe, we see that it took 2.4 seconds with a throughput of 431 kilobytes per second, another substantial savings. Back to the action again. The final programming action is to program the SD card. This is yet another target agent. We use different target agents to manage the on-chip memory resources of the SoC. We are employing the same Ethernet method for the data pipe. Let's run this action. The sequence is the same as the previous action. By using various target agents, we don't use DDR. This implementation prevents any roadblocks that might occur because of the DDR initialization or other problems. The programming is complete. The programming took 0.2 seconds with a throughput of 4.8 megabits per second. One final time back to the actions. You might be wondering, can I run the processor fast programming actions from the ScanWorks interface? The answer is yes, and shown here. The reason I used the developer for running the action was to have more immediate response via the terminal to the target. To ensure the maximum performance, when in the ScanWorks interface, the data is not sent back to the user until all the steps have been executed.
Alrighty, so that is the end of the video presentation, at least in terms of the demonstration. So the demo showed that ScanWorks programming toolbox where each of the technologies could be applied. And that's the representation within this particular block diagram to show you just a high level view of where the tools were applied. Now more detail from the video. The binary image that we used in this test was 1 megabyte with randomized content. We kept the T clock constant throughout the demo. In the first entry in the chart is the standard JTAG programming model. The T clock rate is determined by the slowest device in the chain. And 30 megahertz is an exceptionally high T clock rate, but the scan chain in the demo had only one device, and it supported the 30 megahertz clock rate. The FFP short chain reprogrammed the FPGA scan length from 1,078 cells to just 7. The SPI DIO used the SPI DIO pins on the RIC 1400 JTAG cable to program the flash device connected to the PMOD header. The PFX programming using the target agent executed in the on-chip memory running at processor speeds, and the JTAG was the data pipe. The FFP programming, the FPGA with a flash player logic to control the SPI bus running at the FPGA clock speeds. The PFX programming here with Ethernet was used for the data transfer and the TFTP server running on the host. The SPI Direct used the FPGA with the RIC 1400 and running at the clock speed of the FPGA within the RIC 1400. Each method can have constraints based upon the UUT design. So let's recap. We've demonstrated 7 different ScanWorks actions to address the challenges of the increased technology complexity, expansive software growth, and all accomplished via in-system with greater programming performance. The UUT design will ultimately determine the speed at which the device can be programmed and which programming technology is best suited. These solutions that we've shown here can improve development time and production beat rates. The lower cost can be achieved with ScanWorks onboard solutions than offboard implementations. Here's some resources that are available for you for BST, that it's out on our website, for FFP out on the website, as well as PFP. In your handouts, you can grab that electronically and go to those pages and learn even more about these technologies if you're interested. And so with that, I think we're ready for some questions. Alan, what do we get?
All right. Thanks, Larry. Great demo, by the way. All right, over to the questions. And just a reminder for the audience, feel free to continue to submit in the remaining time, any additional questions in the questions panel. Larry, our first question is, what was the difference between SPI Direct and SPI DIO?
Great question. So SPI Direct uses FPGA resources that are within the RIC 1400, and that uses the SPI flash IP, where the SPI DIO uses the DIO signals within the ScanWorks, in this case, the RIC 1400, but it is supported in all the ScanWorks controllers, and that is embedded within the cable interface from the controller to the UUT.
Okay, all right. Second question then is, how does this compare to just flashing the device using U-boot?
Okay, PFP uses the on-chip RAM, where U-boot is normally booted from flash and loaded into DDR memory. There's a couple of issues potentially with that. Is the DDR memory configured? Does it work properly in terms of the controller? And U-boot actually copies itself once it's been initialized into another segment of memory. So with the PFP implementation, where we're directly going to the processor, the only thing that really has to work on the target system is the processor.
All right. Okay, let's see. Third question is, this one may be a little bit tongue-in-cheek, Larry, but I'll give it to you anyway, right? Is this a good way to program the 256 gigabyte flash device inside my iPhone?
Yeah, that's a good question. So based upon that criteria that you've set here, since it is in fact embedded flash, it depends upon whether it's NAND or NOR flash, but if it's that size, it's likely to be NAND flash, then the short chain IP would be a solution that you could use there. It depends upon the image size, as you might imagine. Even though the device is 250 gigabytes, it's going to take some time, but the question is what are you physically programming? Are you programming an OS? Are you programming just data? Or is this something that's just being used as a data holder for user data? So the best implementation that I can think of at this point would be using the short chain IP.
Yeah, my 2 cents worth, Larry, is there's probably better ways to jailbreak your iPhone than this.
Very true.
Or what it might be worth. Anyway, it looks like it's we're up to about 45 minutes here, Larry. So I think we're running out of time for answering some of these questions, although that last one was a pretty good one. Yeah, is there anything else that you want to cover before we wrap up?
Sure. I'd just like to thank everybody for attending today's webinar. I hope you found it informational and there's some data that you can extract from it. If you have any questions, you have my contact information on the screen or in the handouts. Please feel free to reach out to me with any questions that you might have that weren't addressed because of your shyness or just because of the lack of time. Thank you, and appreciate everybody's attendance.
Great, thanks, Larry, and thanks everyone for attending the webinar today. If you have any other questions, please be sure to make a note of Larry's contact information right on the previous slide. Larry, could you go back? Great. And just as a favor, as you exit today's webinar, please, we appreciate it if you'll complete the survey that's on the back end and provide your feedback. You'll also receive a follow-up email within 24 hours with a link to review a recording of today's webinar. So on behalf of Asset Intertech and Larry Osborne, thanks everybody for joining us today, and have a great rest of your day.